This section explains what the opening chapter on categories, functors, and natural transformations exists to accomplish. The chapter exists to legitimize one definition, and the other two are scaffolding built downward to support it. Eilenberg and MacLean wanted naturality, the idea of a construction defined without arbitrary choices, made precise, so they invented natural transformations. A natural transformation needs a source and a target, so they needed functors. Functors in turn need sources and targets, so they needed categories. The dependency order is the reverse of the presentation order. The dependency order is the reverse of the presentation order, and that inversion is the chapter's thesis. The anchor is the double dual. A vector space B is isomorphic to its double dual without choosing a basis, while V is isomorphic to its single dual only with such a choice. The two situations share an isomorphism class, but differ in epistemic status, and only the arrow-level language can state the difference. The maps between the maps were the point from the beginning. This section carries the chapter's single move. An object is what maps into it. C. A universal property of an object, C, is an identity. The object C represents a functor to the category of sets, and the Yoneda lemma guarantees that this representation pins C down to unique isomorphism. Riel's anchor is the complete graph, Kn, which represents n colorings. A coloring of a graph G is exactly a homomorphism from G into Kn. Symmetries of Kn are exactly permutations of the colors. The word universal then collapses to a synonym, initial or terminal, in the category of elements of the represented functor. One primitive wears three costumes: universal property, representable functor, and initial or terminal object. Mazur's epigraph compresses the thesis. Deal directly with the functor representing X. This section explains limits and colimits, the one construction behind every example the chapter opens with. Products, spheres cut out by equations, projective space as a quotient, cell complexes glued from disks, each is one move performed twice. A limit is the universal cone over a diagram. A colimit is its dual, the universal cone under the diagram. Universal means representability engine as chapter 2. Now run on diagram. F from any object into the limit of a diagram. F correspond naturally to the cones from that object over F. So the limit is whatever object the cone functor already points at, unique up to unique isomorphism. This is the same representability engine as chapter 2. Now run on diagrams. The chapter's quiet punchline follows by Yoneda. Computing limits in the category of sets suffices to derive limit formulae in every category. One shape, two orientations, all of the constructions, infima, kernels, and gluings shed their separate definitions and land as instances of a single pattern. This section explains what an adjunction is, the structural primitive of chapter 4. An adjunction is a translation contract between two categories. It consists of a pair of functors, F carrying the category C into the category D, and G carrying D back into C, such that maps from f of S to V correspond naturally to maps from f of S to V, correspond naturally to maps from S to G of V. Each side answers questions posed in the other's language, optimally and in one fixed direction. The chapter's anchor is the free functor sitting left, adjoint to the forgetful functor. A linear map out of the free vector space on a set. S is exactly a function out of S because a basis is precisely the data a linear map needs. Kahn's tensor-Hom duality is the same contract. The asymmetry is the point. The forgetful functor U has no right adjoint, which is why the word free is unambiguous here, and why a free field fails to exist at all. This section explains what a monad is at the structural level and why it can stand in for a whole category of algebras. Stand in one category and forget that the other side of an adjunction exists. What remains visible is the composite endofunctor, UF, the unit, and a whiskered conate. Together, these form a monad. Riel's framing in Chapter 5 reads the monad as the shadow, an adjunction casts on the home category. The chapter's thesis is that this shadow is unexpectedly often enough. The forgotten category abroad can be rebuilt from it, with its objects recovered as algebras for the monad. A monad is thus a syntactic presentation of algebraic structure, carried entirely by the category it acts on. The boundary is diagnostic. Monoids, groups, modules, and compact Hausdorff spaces are all algebras over the category of sets. Fields are not, and that is exactly why their category misbehaves. This section gives the single move behind the whole chapter the best approximation from the wrong side of an inclusion. Extending a functor f from a category C to a category A along A functor K from C to D rarely works on the nose, since D may identify arrows that E keeps distinct. So you ask instead for the universal natural transformation between F and a functor out of D. That universal pair is the Kahn extension, and its left and right forms are the two partial adjoints to restriction along K. Riel opens with the function 2 to the power x. Each step of the extension from the natural numbers to the integers, then to the rationals, then to the reals is this one move, and the last step is forced by completeness rather than by a formula. Maclane's slogan in the title is literal. Section 6.5 recovers limits, adjunctions, monads, and the Yoneda lemma as special cases. One construction, every concept? This section walks through the chapter as a refutation by exhibition. To the recurring claim that category theory has no theorems, Riel answers with 5 drawn from the book's own Harvestaposes and the Freyd-Mitchell embedding theorem. The preservation of limits and colimits by adjoints, the adjoint functor theorems, monadicity, and the Kahn extension formulas. To these, the chapter adds Maclane and Kelly coherence, the Freyd and Lindster unit interval, Giraud's characterization of Grothendieck toposes, and the Freyd-Mitchell embedding theorem. The shade they share is the Riel thesis. A categorical theorem characterizes, it says a structure is exactly the thing with a given universal property. The interval is the terminal coalgebra of the functor, sending x to x wedge x. A topos is exactness plus size conditions. Johnstone's inversion closes the chapter. Embedding theorems are a license for greater abstraction, and forgetting structure is how you see the essential.